morning. So in today's Sloss talk, I would like to share some of the results from my experiment earlier this year, and it's about the evolution of the crystal structure of hydrous light at high pressure up to 33 GPa. And just a short introduction about light. Light is considered to be the most abundant mineral in alpha transition zone, and is also nominally anhydrous mineral, which means it can contain hydrogen in its crystal structure. And because of this hydrogen, hydrous light is quite different from anhydrous light. It's different. Anhydrous light is strictly orthorhombic, but the hydrous light show a little monoclinic. The difference between two symmetry is largely the monoclinic beta angle. So if this angle is 90°, it's orthorhombic. But if this angle is deviated from 90°, we show monoclinic. And people assume hydrous light is orthorhombic. This is probably true at room pressure and maybe pressure below 10 GPa, because the previous result indicate that the beta angle is very close to 90°, and this angle does not change with pressure. However, people also, because no data available, people also assume this is the case, and beta angle does not change in the whole pressure range. So that's why we did experiments. So in our results, we actually show the beta angle change with pressure above 10 GPa. So the figure I'm showing you here is the result. The x-axis is pressure and the y-axis is the monoclinic beta angle. And we can see above 10 GPa, the beta angle increase with pressure. So this indicates for hydrous light at high pressure is probably monoclinic, but not orthorhombic. So how is this going to change our understanding about hydrous light? So this is going to change how we get the equation of state. So high pressure study usually get equation of states by fitting the volume versus pressure data. But the volumes largely depend on what kind of symmetry or space group we choose. So in order to see the difference, I fit the data, the X-ray diffraction data with two different symmetry. The blue lines obtained by using monoclinic symmetry, and the red lines using orthorhombic symmetry. We can see the two lines are not overlap with each other, which indicate that orthorhombic symmetry does not represent the true nature of light, and the equation state is somehow deviated from the right ones. And from this, we probably need to revisit some of the equation of state published in the early year, especially those equation state obtained above 10 GPa.